Okay, hi guys, so let's continue on seeing more on Kirchhoff's law. So suppose we have a reaction that A moles of A reacting with B moles of B forms C moles of C. So in this case we can write that delta R CPM would be equals to C times CPM of product C minus A times CPM of reactant A minus B times CPM of reactant B. Okay, so similarly if we have this reaction that 2 moles of H2G reacting with O2G and forming 2 moles of H2OG. So in this case, let's say H2OL we have. So even if it has different phases, still the equation for CPM delta R CPM would still be valid, and it would be 2 moles of CPM H2OL minus 2 moles of CPM H2 minus 1 mole of CPM O2. Okay, now with the same we can also have the analogy for delta RH. So delta RH can be written as summation of RP delta HM. HM is the molar enthalpy of products minus summation of R, this is RRP not RR, minus RR delta HM R. So which is summation of stoichiometric coefficient times the molar enthalpy of products minus summation of stoichiometric coefficient of reactants times the molar enthalpy of reactants. Delta HM is molar enthalpy. Okay. Next, we can also say that delta RH is equals to summation of RP delta F H of products minus summation RR delta F H R, where delta FH is enthalpy of formation. Okay, so similarly delta F HP would be enthalpy of formation of products, and delta F HR would be enthalpy of formation of reactants. Delta FH is enthalpy of formation. Okay, and similarly at standard state we can write that delta RH naught would be equals to summation of RP delta F HP naught minus, this is delta F H naught HP minus RR delta F H naught R. So this would be the enthalpy at standard states. Okay, next let us see some examples on the same. So we have first one as, let's suppose half moles of N2G reacts with 3/2 moles of H2G and forms NH3. So in this case delta F H naught NH3G would be the enthalpy of formation of product, and now we'll write the equation that delta RH naught is actually equal to delta F H naught NH3 minus 1/2 delta F H naught N2 minus 3/2 delta F H naught H2. Okay, And just an important note here that delta HF naught at standard state for elements is considered to be 0. Okay, or delta HF naught is also considered 0 for substances which are stable in nature. For substances which are stable in nature. By stability in nature, we mean which are in native form in the nature, which are in native form. Okay, so we can see that N2 and H2 are in the native form in the nature or in the elemental form. So we can say that these two terms would be 0, and in this case delta RH naught would be simply equals to delta F H naught of NH3. This is just at standard states. Okay. Now let us see another example. So we have N2G, again this is formed in the native state in the nature, plus 3 moles of H2G converting into 2 moles of NH3G. Okay, so in here we can write that delta R H naught would be equals to 2 times delta F H naught NH3. Okay, let's take another example. We have half N2G reacting with 2 moles of H2G and half moles of Cl2G forming NH4 Cl in solid state. So delta R H naught for the reaction would be simply equals to delta F H naught, which is the enthalpy of formation of NH4Cl. Okay, and delta F H naught for this would be 0, for this would be 0, and for this would be 0. Why? Because they are found in their native form in the nature. Next example is, suppose we have NH3G reacting with HClG and forming NH4Cl in solid state. So in this reaction we can say that delta R H naught would not be equals to delta F H naught NH4Cl. Okay, and why would this not be the case? Because these two are not found in the nature in their elemental forms, or these two are simply not in the elemental form. So rather delta RH naught would be written as delta F H naught NH4Cl minus delta F H naught NH3 minus delta F H naught HCl. Okay, so this would be the delta RH naught for the reaction. We have to subtract delta F H naught for the reactants as well, as these two are not in their elemental forms, because they are formed from different elements, from nitrogen and hydrogen in this case, and hydrogen and chlorine in this case. Okay, so just writing it in notes here that as NH3 and HCl are compounds, or in other words not in their elemental forms, this implies delta F H naught cannot be 0 for these compounds. Okay, now let's discuss the rules of delta R H naught. Okay, so first is, for pure elements we can write that delta F H naught is 0. So delta R H naught for nitrogen gas is 0, delta R H naught for FeS is 0, and delta R H naught for, let's say, bromine in liquid phase would also be 0. Okay, as these are found in the native state, as nitrogen is freely available in the nature at standard states in its gaseous form, delta RH naught for Fe is 0 in its solid phase, and for bromine At standard states, it is liquid at the standard states, hence delta RH naught for bromine liquid would be 0. But on the same side, we can write that delta not RH, it would be delta F, enthalpy of formation, delta F. Okay, so similarly delta F naught, delta F H naught for N2L would not be 0, because at standard state nitrogen is formed as gaseous molecule, gaseous element or molecule. Okay, it's not found in the liquid phase, hence delta F H naught for N2L at standard state would not be 0. Similarly, the same can be written for Fe in liquid phase is not 0. Heat of formation, enthalpy of formation of Fe in liquid state at standard state is not equal to 0. Similarly, enthalpy of formation of bromine in gaseous phase at standard state is not equal to 0. Okay. Next, let us see that if N2G converts itself into N2G, then this is an example of null reaction. Okay, so in this case delta F H of formation of N2G would be 0. Okay, but if on the other hand, if we see the formation of, let's say, N2G into N2L, then this is not a null reaction, this is a completely valid reaction. Okay, so here we can have delta RH naught would be equals to delta F H naught of N2L. Okay, so with this we come to the end of this lecture. In the next lecture we'll be seeing some more examples on the enthalpy. So till then, good luck and goodbye.